Hi everyone, welcome to Random Thoughts with Alex. This is part 3 in my series about the Lorentz Aether model. And in this episode we're going to look at simultaneity in absolute space and the Lorentz contraction. I'm going to try to show how a proper understanding of simultaneity in the context of an absolute space is necessary to fully understand the Lorentz contraction within the Lorentz Aether model. So in a nutshell, what are we going to look at? Well, let me start by summarizing what I said in part 1, my outline of the Lorentz Aether theory. The Lorentz Aether theory aims to be mathematically equivalent to special relativity. This is not something we are going to need in this video in particular. Second, the Lorentz Aether theory assumes absolute space and absolute time measurable, at least in principle, by objects at rest. Third, it assumes that velocities are additive as they are in Newtonian mechanics. Fourth, it obeys the principle of relativity but as an emergent law. In other words, something that we find in measurements but not as a fundamental law, not as an axiomatic property of space-time. It's just something that we observe systematically in every measurement we do. On the other hand, the equation E equals mc squared is going to be taken as an axiom or a law of nature. And the Lorentz Aether theory assumes that space is Euclidean, so we don't need a Minkowski space to fully understand relativity. So what am I going to discuss in this video particularly? Well, first of all, what exactly is the problem we're trying to solve? Essentially, we're trying to understand the Lorentz contraction, and for that we need to fully understand simultaneity. Second, we will look at how Einstein defines simultaneity when objects move with relativistic speeds. We're going to look at how that definition changes in an absolute space. So the definition doesn't change, the interpretation of the definition changes. Next, we'll look at how Einstein's definition affects the measured length of moving objects in absolute space in comparison with its actual length. Next, we'll see how that relates to the principle of relativity. So we will apply the principle of relativity to constrain our observations or what we can deduce from the previous sections. And then finally, we'll see what we can conclude from this thought experiment. So first of all, what is the problem we're trying to solve? Well, imagine you are standing at a platform at a train station. There's a train right in front of you, or you're in a train, and there is a passing train. When the two trains are at rest, they would have the same size, but in this case, each train is indicated by a ruler. We can use the train as a ruler, or we can replace the trains by rulers if we want. But if they're both standing still, they are the same size. If one of them is moving, then the observer that is standing still with the train that is standing still will see this moving train as if it is shorter. That's something we know from the theory of relativity. We also know from the theory of relativity that if you are moving with the train, you will see the train that is standing still on the platform as being smaller than the moving train. And this observation, the fact that regardless of who does the observation, you always get the same result. It's always the one that is moving relative to the observer that is the smaller one, the shorter one. That really suggests that space is relative and not absolute. So we need to understand how this can be reconciled with absolute space for the Lorentz Aether theory to make any sense at all. And so that is the purpose of this video. Along the way, we will derive the Lorentz contraction. So, what is the Einstein's definition of simultaneity? Essentially, imagine you are an observer and there are two lightning strikes, and we want to determine if these two lightning strikes are hitting simultaneously. How do we measure that? Well, we place the observer right in the middle between the two lightning strikes. We wait for the light from those two lightning strikes to reach the observer. If they reach the observer at exactly the same time, then we say by definition that these two lightning strikes occurred simultaneously. I say by definition because we are going to use this principle, this definition, regardless of whether the observer is moving or standing still. There we go. The definition remains the same when the observer is moving, which means that the definition is purely observational. We are not making any assumptions of how the light behaves relative to a moving observer. We are stipulating that the light moves at a constant speed regardless of the observer, and we're incorporating that into our definition of simultaneity. And when you read Einstein's little book on relativity, you will see that he's very insistent, very precise in how he formulates that. This constancy of light is something he stipulates. It's not something that he observes. That comes later. So, if the observer is moving, and for convenience I'm showing the lightning bolts also moving with the second observer, because they're instantaneous, so it doesn't really matter whether they're moving or not. The observer is going to assume that they would move with them. But what's happened is in absolute space is that the two light signals coming from those lightning bolts, the one that is moving coming from the front, the direction that the observer is going to reach the observer first, and the one that's behind the observer that has to catch up to the observer is going to reach the observer later, because by the time the two lightning strikes, the light from the lightning strikes reach each other, the observer has already moved to a different location. And that means that simultaneity depends on the observer, which is what Einstein said. According to Einstein, there's no way to determine which of the two observers is right. They're both right in their own way because they're both using themselves as the frame of reference. And Einstein concludes from that time is not independent of space, because we cannot tell who is standing still and who is moving by any accounts. All of them could be standing still from their own point of view. How does that change when we consider absolute space? If we believe that space is absolute, then one of the two observers must be wrong about their assumption that they're standing still. Only one of them can be standing still in absolute space, and therefore the other one must be moving in absolute space. And whoever is moving in absolute space is wrong about their conclusions. They're using the definition correctly, but what they're describing does not actually correspond with reality. You could speculate that the microwave background radiation from cosmology provides an objective frame of absolute rest, because there is a frame of reference where the microwave background radiation is isotropical, at least at the largest scale. So that would be my suggestion on how to define absolute space, and there have been people who have made that suggestion before me. So I conclude that the relativity, say the relativity of space and time, the relativity of simultaneity, is an artifact of not knowing which frame of reference is the absolute one, the one at absolute rest. So, what does that mean for the length of two objects? let's take a look at the exact same experiment, the thought experiment that Einstein describes in his little book, but now we're going to describe it in absolute space and time. So what I'm showing here is, first of all, the time is moving up, so the vertical arrow upwards is the time. It's as if we're looking at a film of a occurrence of one train passing another, and we're rolling out the tape of the film and we're looking at what we're seeing. It gives us a record of what has been shown. So early on, at the beginning of the thought experiment, so at the bottom, we have an observer who is sitting in a stationary train in absolute space. He's sitting right in the middle, so he's at equal distance from the front and the back of the train. When the train is approaching the observer, he sends a light signal to both sides of the train. When those two light signals reach the ends of the train, they activate cameras that take pictures of the alignment of the two trains. In this case, because the moving train is shorter than the stationary train, the photos will observe that according to the alignment, the moving train indeed is shorter than the stationary train. Let's assume that the cameras use a flash to take the picture so that the observer can wait for the two flashes to come back, and if they come back to the observer simultaneously, then according to the definition of simultaneity, those two pictures were taken at the same time simultaneously from the perspective of the observer. So the observer confirms that the moving train is shorter than the stationary train, as I indicate here. So how does that look when the observer is in the moving train? So now the observer is in the shorter train. He's in the middle of the shorter train and sends out two signals simultaneously. The signal that goes to the back of the train takes a picture before the signal at the front reaches the front of the train, and when that picture is taken, the back of the train of the moving train has not yet reached the back of the stationary train. Later in time, the signal going forward activates the camera at the front, takes a picture, and shows that now the front of the moving train is past the front of the stationary train. Again, the two flashes of those cameras reach the observer at the same time. That means that from the perspective of the observer, by definition, those two pictures were taken simultaneously. So from the perspective of the moving observer, the two photos give a genuine idea of the relative size of the two trains. He sees that the back of the train is behind the back of the stationary train, and that the front of the moving train is in front of the stationary train. In other words, the moving train is seen by the observer as longer than the stationary train, despite the fact that it is actually shorter. And that is the main conclusion so far. So far we've done only qualitative analysis. We will now move on to quantitative analysis, but let's first draw some conclusions. An observer at rest sees the size of objects the way they really are. The moving train seems longer than it is from the perspective of an observer who is moving with the train, and the reason is because the photos were not taken at the same time. The train is objectively shorter than the stationary train, but the observer can't see that because of how the light plays with the alignment of the train. So it is possible for a moving train to seem longer than a stationary train when it is actually shorter than the stationary train. Okay, so now we're going to run some numbers to see how that actually works in terms of equations. And for that, we need to be a little more precise in our formulation. So instead of drawing trains, I'm going to use a chart like is shown here, like a Euclidean chart. Again, time is running vertical from down to up, and so these dark red lines that are parallel to each other represent a stationary train as time goes forward. We assume that the train has a length of 1, so that it starts at minus 0.5 and ends at it starts at minus 0.5, ends at plus 0.5, the total length being 1. The bright red line is the center of the moving train. So there is a train that is going to pass the stationary train. The observer will be in the middle of that moving train, and the red line, the bright red line, is the path of the observer in space-time. So at negative time, the person is at a negative location. At time 0, the person is at location 0. At positive time, the person is at a positive location on our x-axis. So as I indicated, the axes are absolute space and absolute time. For the absolute time, we multiply the time by the speed of light so that we would get time expressed in meters. So when I say 1 meter of time, what I mean is the time needed for light to travel 1 meter in absolute space. The horizontal axis is location. Okay, so now let's add the moving train to the stationary train. Because the train is moving, it is shorter than the stationary train. It's indicated by these bright red lines, and of course, because the train is moving, we see it's going at an angle. It's not going straight up. In the figure, I used a velocity of 0.6 times the speed of light. According to the Lorentz contraction that we know, that means that the train should have a length of 0.8 if it had a length of 1 when it's standing still. Now, we're not going to worry about the actual length because we're going to calculate that. It's just for the purpose of the drawing. It's good to have the numbers in mind. So we will call the length of the moving train L, and we were going to calculate L so that we can actually derive the Lorentz contraction. However, the person who is traveling with the train is going to think that the length of the moving train is 1, because if they have a ruler with them and they measure the length of the train, that ruler will contract with the train, so there's no way for that person to tell that the train is shorter than it used to be. So in absolute space and time, the observer moves according to the equation x equals v times t. The front of the train is a distance L over 2 in front of that, so the location of the front of the train, x, is v times t plus L over 2. The back of the train is a distance L over 2 behind the train, behind the observer, so that is vt minus L over 2. We're going to need these equations to do our calculations. So we can add the light rays that are sent to the back and to the front of the train, and that is done by these green dashed lines, and then the camera will respond with a light flash that will send a signal back to the observer. Same with the camera at the front. We assume here that the cameras are located on the stationary train and that the alignment will be measured with respect to the moving train. So for purpose of symmetry, we assume that the light signals at the beginning of the thought experiment are sent at the time minus 1 over 2c. We could have chosen any time, but this gives us a nicely symmetrical result, and that will simplify the calculations. So at that time, the observer is at a location x equals v times t, so that is minus v over 2c. The backward light signal is moving backwards with a velocity c starting from that location. So x of the backward moving light is minus v over 2c minus c, the speed of light, times the time elapsed since the signal was sent. So that is t minus 1 over 2c. The forward light signal is the initial location of where the light was sent from plus c times the elapsed time. So now we need to figure out when these light signals correspond to the locations of the back and the front of the train. So we have the backward moving light signal. We're going to clean up this equation a little bit. The first term stays, v over 2c with a minus sign. The second term will be minus c times t. For the third term, we can cancel out c and we can cancel out minus signs, but there are 3 minus signs, so we get minus 1/2. The back of the stationary train is x equals minus 1/2. So the light signal coincides with the back of the train when the x of the first equation equals the x of the second equation. So when we substitute, we get minus 1/2 equals minus v over 2c minus ct minus 1/2. So clearly we can cancel out minus 1/2, and then we can solve for t, and we get t equals minus v over 2c squared. So the time at which the light signal reaches the back of the train is minus v over 2c squared. Now we're going to determine the location of the observer, because we need to know how far is the observer from the back of the train when that picture is taken, because that determines the measurement that the person is going to observe. So the location of the observer again is x equals vt. We have the time that the back of the train is reached. We have the location. So if we substitute the time that the light reaches the back of the train into the equation for the location of the observer, we find that the observer is at location minus v squared over 2c squared at the time the picture is taken. The v squared over c squared might be intriguing at this point, because that's something that also occurs in the Lorentz contraction. Now we do the same thing again, but with the light signal that's moving forward. And the only thing that changes is a minus sign that becomes a plus sign, and the minus 1/2 becomes a plus 1/2. So I can go through that fairly quickly. We clean up our equation. We set it equal to x equals 1/2 to find the point at which, the time at which the two coincide. Again, we cancel out 1/2, and we find that the time is plus v over 2c squared. Again, nicely symmetrical, and that's why the initial time was chosen the way it was. Okay, now that we know the time that the second photo was taken, we calculate the location of the observer at that time, and we find that it is plus v squared over 2c squared. So here, a summary of the results that we have found so far. We have taken a picture at the back, we've taken a picture at the front. The back of the stationary train is at minus 1/2. The time that picture was taken was at minus v over 2c squared, and the location of the observer at that time was minus v squared over 2c squared. The picture at the front end of the stationary train was taken at location 1/2 at a time v over 2c squared, and the observer was at location v squared over 2c squared at that time. Okay, before we do any further calculations, let's check that the observer sees the two photos as being taken at the same time. In other words, we need to check if the two light signals reach the observer at the same time. This will be relatively simple because of the symmetry that we've imposed. Again, we could have taken any starting time, the result would have been the same. But the light coming from the picture taken at the back, the camera activated at the back of the train, will be the location when the photo was taken plus the speed of light times the time elapsed since the picture was taken, which is minus 1/2 plus ct plus v over 2c. The location of the observer, which is v times t. We want to know when the light signal coming back to the observer coincides with the location of the observer. That means x must fulfill both the equation of the light signal and the equation of the observer. So we set the two equal to each other, and we find that Vt equals minus 1/2 plus Ct plus V over 2c. We can solve that for the time, so we take the two terms that have the time in them together, and that gives us t times c minus v. And the remaining terms go to the right hand side, which is 1/2 minus v over 2c. If we put that on one fraction, we get c minus v over 2c. And we see c minus v as a factor both on the left hand side and on the right hand side. So we can cancel that out and solve for time, and we get that the time equals 1 over 2c. That's the time when this light signal coming from the back of the train reaches the observer. Let's do the same thing for the signal that went to the front, the picture that was taken at the front, and the light that comes back from the camera to the observer. Again, we have our data, the location of the returning signal as a function of time, the location of the observer. Those two have to be the same, so we substitute. Now we have that time times c plus v equals c plus v over 2c. And when we cancel out c plus v, we find that the time that the signal reaches the observer is 1 over 2c, the same as the time when the other signal arrived to the observer. That means that the observer will indeed observe these two pictures as if they were taken at the same time. Now the observer must measure the locations of the two photos with respect to the moving train. So the rear photo was taken at x equals minus 1/2 at a time when the location of the observer was x equals minus v squared over 2c squared. And so the difference between the two is the distance between the observer and the photo, which is 1/2 times 1 minus v squared over c squared. And that's becoming more and more intriguing for people who already know the result. The front photo is taken at x equals plus 1/2. The observer is at location v squared over 2c squared. So the distance between the two is the same, 1/2 times 1 minus v squared over c squared. So the sum of these two seemingly simultaneously measured distances is 1 minus v squared over c squared. That's not the actual distance between the two photos, but that's how the observer will see it, except for the fact that the train is contracted. So the distance as it would be observed if the train was not contracting would be 1 minus v squared over c squared. But because the train is contracted, the train has a length L, but the observer thinks that the length of the train is 1. So he sees the train as a factor 1 over L as long as it actually is. So he will also see the distance between the two photos as a factor 1 over L as long as the actual distance. So we find that the measured length of the stationary train according to the moving observer is 1 over L times 1 minus v squared over c squared. That is our result. Now we can invoke the principle of relativity. And that's what Einstein did too. He did not really prove things from first principles. He just used the principle of relativity as a first principle and reasoned from there. So we're doing the same thing here. If the principle of relativity holds, then the observer on a moving train should see the stationary train as the same size as the observer on the stationary train sees the length of the moving train. But the observer on the stationary train sees the length of the moving train the way it really is. So he sees the length L. As a result, the observer on the moving train must see the length of the stationary train as L. And we've just calculated that what he sees is 1 over L times 1 minus v squared over c squared. That means that L must be the same as 1 over L times 1 minus v squared over c squared. So when we solve that for L, we get that L equals 1 minus v squared over c squared square root. So the square root of 1 minus v squared over c squared. And that is the Lorentz contraction. And there we go. We have derived the Lorentz contraction in absolute space using the same principle of relativity as Einstein used and using the same definition of simultaneity as Einstein used. So we find that indeed an observer on a moving train will see the stationary train as shorter than the moving train, in spite of the fact that the stationary train is actually longer. So what do we conclude? First of all, an observer in absolute space at rest sees the size of objects the way they really are. A moving observer in absolute space will see the size of stationary objects shorter than they really are. For the principle of relativity to hold in absolute space, the observed contraction of objects, real or apparent, must be exactly the Lorentz contraction. And this is something we will explain mechanistically in a future video. Right now, we're kind of doing a lot of hand waving and using the principle of relativity to do these calculations, but we will see in a later video that we can actually derive that mechanistically. But we have to establish the principles first before we can do that derivation. The next video, so part 4 in this series, will be time dilation in absolute space. So there we will do similar thought experiments at what we're doing in space here, but now we will do them in time, and that will give us the time dilation from Lorentz theory. I hope you find this video interesting. If you do, please like and subscribe, and I'll see you in the next video.